Hello, gentlemen. Today we're going to answer a question, but we're going to do it in an actual real-world test. So, in this amplifier is a different style of flyback circuit. Now, let me explain to you what's going on. From time to time, I'll have somebody show up that's got enough drive and initiation where I want to actually teach them something, right? And they really love the hobby. Well, I've had a young gentleman show up into my world here last year before last, and he loves this hobby. And my friend Tony and myself, Tony, aka Fat Boy over at ICA, we've taken this young kid on as a student, right? First thing Tony did was give him enough parts to go build like 52 pills and said, here, go work on this for a hot minute. So he'd go off, build a couple 2 pills, come back, they'd test them, so on, and then it's just slowly grown. Well, now he's branching out and he's starting to do some of his own builds, and they are top notch. But then he's also started to take on the repair side of the business, because let's face it, I got a ton of work, right? And there's a ton of people out there that need to have their stuff fixed, and if they can't get their stuff fixed, they'll go find something else to do, and all of a sudden the hobby dies. So we need more repair technicians. Well, he comes to me last week and he goes, man, have you had a chance to play with the Dave made amps? And I said, yes. And he goes, what do you think of their flyback circuit? And I said, and he goes, what do you mean? I said, well, I built this and I tested this. And I said, I wasn't too overly impressed. And I'm going to demonstrate to you guys what made me not be impressed. Okay? So I thought, you know what, the next time I build an amp, I'm going to build that flyback suppression circuit or pass-through circuit or feedback circuit or negative compression circuit or overdrive coupling circuit or however you guys want to refer to it. Because there's about 17,000 names for this one circuit. The way I look at a flyback is it works in both ways. You have your output transformer and your input transformer, and it allows us to have a coupling effect that takes place between the input and the output and the output and the input, and it protects the component from 2 different directions. One of the things that it does is it is a harmonic suppressor in a certain format, only in a certain angles of operation in the transistor. Big fancy words, I know. The other way I like to think about it is that the transistor can only absorb so much drive. Per the data sheet, 12 watts. We all know it can take much more than that, but can it really? Your flyback circuit allows there to be a physical coupling between this transformer and this transformer. The little disc capacitor that's on the end of it blocks the DC voltage that's present on this transformer. Blocks it, doesn't allow it to run this direction. But that 100 ohm resistor, depending on how you look at it, can read 100 ohms or can only read 50. Okay? The RF only sees one side of that. So the total sum resistance might be 50 ohms depending on how you look at it, but you got to think there's 2 resistors in that circuit. What happens when you put 2 resistors in parallel? Oh, resistance goes down. But because this is a push-pull, but then you got to think, this backplate here on this transformer and a backplate on this transformer are technically one piece of metal. So the sum total resistance in the circuit is 50 ohms. It allows the RF that doesn't get saturated into the transistor, a little bit will pass up through that disc capacitor and pass into the output transformer and find another way out of the box. And how that coupling effect takes place can add or subtract harmonics to the box. Now, like I said, I measured this, and I am one of these guys that I'm getting a little bit older in years, and you know what happens when you get old? You start having a little bit of slightly decreased cognitive ability or processing power in your brain. And I said to him, buddy, it has been so long since I've messed with that circuit, I cannot tell you specifically what made me unhappy with it. I said, I just remember it added harmonics to the circuit. And he went, oh, okay. Now the harmonics that are added to the circuit aren't necessarily bad, and I'm going to explain to you about that later. There's a way to have harmonics be present to where they're not going to show up as an issue. We'll cover that here in a hot second. The way and I say this air quote, Dave made, and really who's been putting this more in play is my really good friend who I've got nothing but love and respect for, Chris, down at BM Technologies. And really, I've got nothing negative to say about Dave. None of it, because this isn't wrong. It's just something that I choose not to do. So please understand that I am not in any way saying this is wrong. I'm just saying that me, personally, myself, I don't want to build these into the box. Now, y'all know me. I'm kind of cantankerous. If and when I die, about 30 days after I'm dead, I'll be out here trying to build something. Okay? And what I mean by that is if I see something that somebody else has cooked up, I'm going to snatch that son of a bitch close, I'm going to hold it in my chest, and I'm going to go use it. Okay? So I'm not afraid to test new things. But I have a hard time, being that I grew up in a very ham-based environment and found that a lot of the misnomers in the ham community, once I got older, was actually able to afford real equipment, and a lot of the things that the hams say, and often, oh, it's a splatter box, it's got to be biased, for, otherwise it's going to have harmonics in it. That's not true. Prove that over and over and over and over again. When somebody says that, they're talking to hear words leave their face hole. Okay? Or, man, that guy, he was bleeding on me from all the way up at 100 or all the way down, and this is another thing they always get backwards. All the way up at 160 meters, all the way down to 6 meters. It actually works the other way around, y'all. 160 is low because the wavelength is really friggin' long, and 6 meters is much smaller, so therefore it's way higher in frequency. Once again, talking out their yam holes. If you are receiving that much harmonic interference from a station, supposedly, you might want to think about throwing some attenuation in your receiver, because your receiver's got really cool filters in it that are supposed to allow you to be frequency discriminate. So it only wants to hear in this one little portion of it, and it should throw the rest of the information away. And if you're too close to another signal, it's going to overload the front end of your radio, and you're going to hear it all over the place. So you get raised in that environment in radio, you very quickly learn that, hey, I'm going to set aside everything I thought I knew, and I'm going to go ahead and I'm going to start doing some independent testing. And I'm going to build my own database of knowledge in my head. So, I remember I had this old X-Force 2x4 that I bought from a guy here locally, and that poor box went through a ringer. I've said this on video many, many times. My very first spectrum analyzer, I think I paid $300 or $400 or $500 for it. I bought it from a guy by the name of Wild Bill down in Nevada, and I was so excited. My girlfriend at the time, which turned into my wife later on in life, I was so excited when I left his house. He just happened to be a friend of a friend that we knew that had a lot of electronic stuff. I was so excited because I was like, man, I can't believe I own a spectrum analyzer. I was literally so excited. I was like, yay! And the reason I was so excited is because in my brain, I knew that this meter, the watt meter, doesn't care what goes through it. It only wants to see the energy that's going this direction, and then if you turn the element around, it reads the energy going this direction. It doesn't care if it's on frequency. More is more. If it sees more shit go through it, it's going to show you more power. Is it going to show you if it's on frequency or not? No, you're blind to that. You're completely blind to that. You have no idea where the RF is going. And if you're working into a dummy load, like this bird dummy load here, man, I've used it all the way up into 2 meters, 70 centimeters. I mean, it says stamped right on the front like 0 through 30 megahertz or whatnot. But the dummy load that I'm working into, that's what's connected to this connector here, shows me no resistance. So it's not going to show up as reflected or non-resonant power. It's not. By the way, the only reason we got this watt meter here is because the haters hate. And for a long time they ran around, and the rumor that they cooked up was, well, the reason his watt meter moves over to the corner so quickly is because his dummy load's all messed up and he never shows you reflect. Okay, let's put another $500 watt meter on the workbench just to show reflect into a dummy load that's never going to have any reflect. Whatever. I was excited because for the first time, I was able to see what was going where and why. And then what I changed in here, affected what comes out over here. Now that old Tektronix spectrum analyzer worked great for me for about 4 or 5 years. And then God bless the gentleman at Siglent that came along and said, hey, do you want to work with us? Let's give you some modern test equipment that I wouldn't necessarily say it's more accurate, but I would say that the 1970 spectrum analyzer I bought, I don't know how close into calibration it was. Where that new piece of equipment, it's kind of hard to argue that it's giving me false data. That, and it's an actual test bench piece of equipment. It's not, you know, a spectrum analyzer nano or one of my KC901s, which is still fairly accurate. I haven't seen a whole lot of deviation between my 901 and that, but still. The way this circuit works, instead of being physically attached, it works with a thing called resonant coupling. Okay. It's got a wire, we'll say starts here. It's not the way the RF sees it, but for conversation point of view here, for us in demonstration on the video, there is a piece of wire that runs this direction through the transformer, goes through the output transformer, then comes back around and it connects over here to the other side of this resistor. And then the resistor acts as its balanced load. So the RF can couple to this wire, otherwise be resonant, and it wants to jump from the saturation point of the transformer cores and plates and ride the lightning. It wants to ride the wire, and then it can recouple itself over here on the output transformer. Same circuit, one less resistor, 2 less disc capacitors. Okay, so it's 3 less parts. And I have yet to do the math, but I don't think the number is that much different between the cost of 1 resistor and 2 disc capacitors over about 6 inches of, 16 gauge Teflon coated wire. I digress. I don't know if it's cheaper or not. I can't say that they do this because it's cheaper. I have no idea why they did this. I've never asked. I could probably call Chris right now. He'd answer the phone and I'd say, hey buddy, why did you guys come up with this? And actually, you know what? I think I did call him when I was playing with this years and years and years ago. And he goes, well, because on our spectrum analyzer, it shows cleaner. And I'm like, oh, okay. I didn't get those results. I just didn't. And so I thought, well, let's come do a one-to-one comparison. I'm going to build this circuit into this box. We're going to test the whole thing. We're going to look at it on the air. We're going to look at it on the spectrum analyzer. We're going to look at the input signal. And then we're going to pull this out. We'll just simply unsolder this, take this out, take the wires out, and we'll go ahead and we'll drop in our standard resistor flyback circuit. The other thing the flyback circuit does is it allows us to have a little bit of overload protection, which you can oversaturate the transistor on the input and it's going to kill it, or you can have an output aspect range that's so high, otherwise SWR. Output aspect ratio is a fancy word for SWR per se. It's not exactly it, but it's close enough for everybody to get their visual brain wrapped around. The output SWR can change so radically. Let's say you have a transistor come and blow up over here. Okay. Then the first thing that happens is there's an imbalance that takes place, and this resistor sucks up most of that imbalanced load for like a key and a half. And it tries to balance the circuit. It sees an imbalance of RF, and so this resistor heats up. I don't care if you have a 2 watt, a quarter watt, a 20 watt, or a 100 watt resistor here. The 5 watts burn up just as easily as the 2 watts. And that's why I always find the guys that have the debate about the 5 watt resistors. Oh, you know, the 5 watt resistors don't do, it's pointless, you're hiding imbalance, and let me pull my jock strap up real tight so I can talk in a high pitched voice. And that's what it sounds like when I listen to the argument. Because I've listened to all the arguments. And don't be silly to think that I haven't. Because if there was an advantage to running a 2 watt cheaper resistor, I would do it. Me personally, I like to wrap myself comfortably in my 5 watt resistors. I cuddle up with them in a blankie at night made of 5 watt resistors, knowing that when, I mean, let's face it, a 2 watt non-flame resistant resistor is way cheaper than a 2 watt flame resistant resistor or a 5 watt flame resistant resistor. The reason people use 2 watts is because it's cheap. And it's the bare minimum that you can use in the circuit to where it doesn't burn up when it's in operation, in the flyback, especially in the flyback portion. These input and output resistors don't do squat until there's an imbalance. They just have a summed load that is presented to each one of the poles of radiation that is being passed through this combiner or splitter until there's an imbalance. When an imbalance happens, the SWR for this 2-pill section goes way up. Its load resistance on the circuit and its resonant path goes way out of spec. Well, that outgoing RF might not have a place to go, and it can back up and it'll blow the transistor up. So we put the flybacks, whatever term, insert whatever tech term you want to use, in the circuit to give us another way for the RF to go and be dissipated. The same thing can happen if your coax breaks, your coax connector breaks, your high output SWR, 100% of the RF that's going out comes back, and it gives us another place to dissipate energy to. You will find, because we have the circuit, the output in the input circuit, physically tied together through a resistor, that you can change your output tune and notice over here on your input tune that it's going to be all jacked up. And I have people that are trying to learn how to build boxes call me all the time, and they don't understand why they can't get their input tune down. And I say, okay, well, so what are you seeing out of it for output power? And they tell me, and I'm like, well, man, the reason that you can't get your input SWR to come down is because your output's so far out of whack that the SWR to the circuit, not at your antenna, the circuit internally is so high that the RF can't leave the circuit to go out. It's not resonant, so the power is bouncing back and it's coupling and showing up here as input resistance. Fancy words, if this isn't tuned right, you're never going to get this to be low. RF can travel both directions in the circuit. The trick is to make the output circuit resonant, and the RF wants to go this way. So that's the most I've ever talked about tuning on video, because I feel like every time I come out here and I talk about tuning, everybody goes and then I have to field 1,000 phone calls with everybody trying to implement that inside their amp, which is not what I want to have happen. I'm just trying to explain what we're measuring here. So all we're measuring today is how this circuit interacts with all the other amps. I've built a lot of amps in this particular style. I might change how these wires are laid out. I might change the size of the power wire. But for the most part, these output transformers, these input transformers have been in several hundred boxes at this point. And you, me, the viewing public, me, the builder, are very comfortable with how these work, and we understand that it's accepted. You can put it out there in the world, and that leads us back to our dummy load issue. Okay. In the real world, you cannot tune to a dummy load for the most part. You can, but your antenna is going to be different. Once again, your dummy load will take anything you put into it. Anything at all. It's going to say, woohoo! I'm a TV antenna, let's go! Woo, woo, woo! It's going to get excited. And your actual antenna that you're using for operation is impossible. It's only going to like a little small sliver of frequency that's fed to it. Think about it. When you guys go and you set up your antennas, let's just use the 11 meter guys. And we're talking a mono frequency antenna, and they try to tune the thing for channel 20. By the time you get down to channel 5, your standing wave is starting to rise. And by the time you get to 35, your standing wave is starting to rise. So here in the middle is channel 20. Over here is infinite SWR. Over here is infinite SWR. There's no resistance here, and the resistance to the RF is starting to climb. We blow that out a little bit. We'll say this is 0, and we'll say this is 50 megahertz. That'd put us kind of in the middle here. It'd actually be about here. There's going to be one little spike where it's going to say I'm resonant, and that's your antenna. The rest of this is not going to be resonant. So if your amplifier produces RF that's here, and here, and here, and here, and here, where it's not resonant on your antenna, it's going to show up as reflect. Where it's not going to show up as reflect in your dummy load. That's why I try to tell these guys that come along and want to learn how to do this right away. I tell them the first thing you need to use is a real power supply, real soldering iron, then a real watt meter that everybody universally accepts the numbers that comes out of it, because them things ain't tamper-proof neither. There's yet to be a watt meter that's been built by man, because it was built by man, isn't tamper-proof in some way, right? But universally it's accepted that these are within a 5 or 10% variance of being exactly what exactly is, for the most part. And then the last thing that you really want to get yourself is one of these. You don't have to get this quality, you don't have to get this model, you have to get something to show you where the power is that you're producing and where it's going and in what places in the band that it's putting it. So that is pretty much what we're here to do today. Is I needed to say all of them fancy words and talk all this much to explain to you what I'm wanting to test. And I'm wanting to demonstrate to this young man that there's a lot of ways to skin a cat. Another way to do this is to have a hoop of wire go through this transformer and a hoop of wire go through this transformer, and just have two 100 ohm resistors sitting in between the wires that are going in and out. I've done that. I've built little insulated pads that came off the output transformer and had the resistor hanging on there, and just took a piece of wire, coupled it over, a couple wire, and tested that too. It doesn't matter which direction that you put the flyback circuit. Like you'll notice on Texas Stars, some of the flybacks will go to the input, the capacitor on the flyback circuit, the resistor and the capacitor will go to the input circuit. Some of the other boxes, doesn't matter. They'll put it on the output. You know, it doesn't matter. To the RF, the AC energy, a disc capacitor doesn't even exist. The only reason a disc capacitor is there is to insulate the positive DC from trying to couple with the negative DC here over here and blowing everything up and shedding shit to Mars, and the caps flying past your head like freaking popcorn. This uses a physical decoupling. There's no I don't want to say mechanical trickery, but it's insulated. And it's using the electrical properties of the wire and the coupling of the transformer to operate. I've tried every which way in this particular, for this circuit, for this to work, and I've tested it. And I use what I like the best. I like how it looks on the spectrum analyzer, just saying. Okay, all those fancy words aside, let's go ahead and set this up. I want to test this real quick. Oh, and for all my hammy friends that are out there, if you go and make this wonderful statement to somebody, man, that guy was bleeding on me and interfering with me from 160 to 6 meters. If you have a trap antenna or you're running on a wire, any multi-band antenna, you are going to have huge dips and valleys across the frequency spectrum, where you're going to have points of resonance, probably 40, 20, and so on, 12, 15, 10, and so on, where your antenna is going to be resonant. And so therefore, you're going to have receive slopes inverses of the SWR. So wherever you have a low SWR point on your antenna is where you're going to have your maximum amount of receive gain. If you have interference that's universally the same level across the entire frequency, it's a proximity or signal overload to your radio, and your radio is unable to process it. So when you go and you speak and you use those words like all the way from everywhere, blah, 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 doesn't work like that. You can receive interference across this whole thing. You're not going to have massive spikes. So if the signal level is even all the way across, it's the fact that the signal saturation over here is so much that when you're trying to work right next to it in frequency, your radio can't discriminate from this side noise. It has nothing to do with the amount of power or the frequency that this guy's occupying. It's all about a proximity thing in your receive. Just saying. Okay, harmonic chat over. Let's actually do something. Okay. So I've had several people through the years either suggest I set up my spectrum analyzer their way, or say that my measurement is invalid because the spectrum analyzer wasn't set up right. For a lot of years, I set this up for only about 50 megahertz, and for the most part, we're going to see a lot of the garbage that might be created. We're going to see it somewhere in here. Okay, and I remember one guy said, "Could you at least expand out your spectrum analyzer to enough to where it can do the rest of us some useful data?" And I was like, "Well, what do you mean?" He goes, "Well, could you take it out to like 100 megahertz or something?" Oh, well, yeah, okay, that makes sense. So what we're talking about is this, from here to here, is your window in the universe. So how wide your multi-band receiver is going to be. So we have this set up for start frequency at 0 megahertz and ends at 200 megahertz. Okay, so from 0 megahertz all the way to the 2 meter band, the very bottom of the 2 meter band. Well, if it was about 40 megahertz higher, it'd be in the 2 meter band, right, or just below it. So we're receiving everything all at the same time. Okay. Back to the harmonic reading issue with you're trying to do it with your ham radio. It doesn't work out that well. Your ham radio, no matter what you've got going on the front, unless it's an SDR, only receives a small little sliver of this, and as you spin the dial on the radio, it moves back the receiver back and forth. Another gentleman come along and told me that I didn't have my noise floor set appropriately. This is our noise floor, which is what, 40, 50, 52 dBm down. It's 52 dBs below zero. I like to run it right about here. The reason I like to run it there is because to me, everything that happens down here below in the negative range, to me, doesn't interest me a whole lot. Okay, it's just we're looking at extra noise floor spikes. Now, we're not in the greatest lab conditions here, but we're still in a pretty good setup. We'd want to get this noise floor reduced quite a bit if we were wanting to do lab measurements. And they're insistent that unless I show the bottom end of the noise floor, that there could be some tomfuckery going on. Me personally, all I care about is the positive spikes and how low below zero up here that we are. Now, the International Standard of Measurement does suggest that we want to see this for the negative signal spike compression field that takes place. But most radio operators don't care, okay? I understand all of this. I read all the big books. I understand all the big words. I get it. But I try to use not big words because I hate people that speak in big language to try and make everybody think that they're smart. I'm not smart. I'm a self-taught technician. Okay? I'm not smart. Not even ashamed of it. I am what I am. So I guess we're supposed to set this up so it's right in the middle, or I mean, I've seen one guy where he's doing all his testing and he's got all. So that, me personally, for the sake of today, we'll make it so that the fuzzy line at the bottom, which is the zero signal that we can read to, I'm more concentrated on what the positive signal spikes are and what that quantity of signal is, and I can't read that if I take the noise floor and I crank it up here. I can't see how much saturation in the signal we've got and where it's located at and how much each harmonic spike is. So that's the reason I've got to have this down here, because I actually work with this every day. Right? Now I could change the field view, and then you'll see a lot of guys will set their spectrum analyzer up. So over here at zero signal, and it'll drop, and it curves, and I've got a pretty good grounded system. It's really basic here. to keep from overloading the receiver on the spectrum analyzer. I just use a Bird 43 coupler. It goes through a coaxial dynamics 30 dB attenuator, which I have reading in reverse, by the way. It gives me about another 10 dBs worth of attenuation. So 45 dB I'm down from the coupler pickup, which isn't even a true line sample. It's a passive setup. Then over here is an additional, right here is an additional, what is this? 8.5 dB attenuator between the input, which is this piece of coax here, and the input for the spectrum analyzer. So I've had to compress that signal quite a bit, bleed it off, attenuate it, that'd be another way to say it, actually a proper way to say it, to where I don't overload the receiver and it gives me a bunch of false information. Remember, I'm trying to measure, direct measure in a closed loop system in some situations. I mean, we're going to work in the 800 watt range today, 800 to 1,000 watts. Some situations, multiple kilowatts with a direct coupling, and we're not trying to measure the signal as is after it's been emitted. We're trying to keep this all in a closed loop system, so everything is controlled. I'm not transmitting into the outside air, so I'm just trying to measure that. Hence the reason there's not a lot of noise down here, you know, from the AM broadcast band and all that kind of stuff. That's the reason we don't see a whole bunch of signal spikes in here. Otherwise this would look like a Sherwood forest and we'd be talking about random spikes. So, okay, so for today, we'll set our top reference line at 0, and at the bottom is 55-ish, whatever dBs down. I personally feel that when we get down here into the 40s, down here so many dBs down, I don't even really care about it anymore because it's such a small amount of signal compared to the principal, okay, that it's not going to show up as significant reflect in a real world antenna, nor is it going to have enough emitted energy into the atmosphere to where it's going to interfere with somebody else operating on that frequency that's designated to be there or wants to work it. This is our radio. Hello. Da 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 da. If we were wanting to do more of a bench test, I would probably use a non-microphone element. I would probably do an injected audible signal, you know, like 100 hertz, 200 hertz, something like that. Something that would just saturate the radio. But for today's demonstration purposes, hello, 1 2 1 2. We can all accept, I think it's safe to say, that we can all accept that what we're seeing here is, well, right now we're seeing about 2.5, 3 watts, which is causing a negative 26 dBm signal to be present. What's amazing to me is, like, when we go to talk to Voyager, when the DSN goes to talk to Voyager, and Voyager 1, Voyager 2, and those guys, their signal to noise floor ratio that they're using is a negative 176 dBm down, and they consider that a great day of communication with them guys. The amplification noise jacket systems that they have to use, the amps that they use to be able to bring that signal up out of the noise floor, and the way they're going about notching out that portion of the band and getting the noise that low is just breathtaking to me. I mean, they're down, if this is, let's say, what does this actually read? Almost 60 dB down. They're way down here. So their noise floor is way down here, and they're able, well, it's actually 20 or 30 dBs below that. They're down here at the table height on the scale. So we're working way up here on the scale. 179, I think the last measurement I seen it was out of the Canberra dish down there, which is I think like the second biggest one in the network or third biggest one in the network. It's the one that's got the biggest amplifier on it, the Calistron setup. Which I'd give my left nut to go down and see and sit down and talk with those guys and watch that system operate. I think it'd be friggin' great. Anyhow, they're way down there in the noise floor. It's 179.5 or 6 is the last one I seen, so, which is amazing. Just amazing. Anyhow, we don't see any major harmonics over here. No first or second order harmonics go in this direction that are really measurable for the most part. And definitely nothing going up positively in frequency. So we now know that our input signal is clean, is what we're getting at. I'm probably way overdoing this video, and I don't apologize for that. Okay, so that's the RF coming through the amp. That's just the radio going in this coax connector, passing through, going out, flying by that pickup, working its way through the three bird meters, and then down to the 10,000 watt dummy load. So let's reach in here. We'll plug the amp in, and we'll turn the amplifier on. So the big debate that everybody's going to get to pull away from this, oh yeah, here, let's do some watt meter readings for everybody's viewing pleasure. Okay, so turn a peak kit on, 1,000 watt slug and peak, 1,000 and average, 5 watt slug and reverse, back from the bird, 10,000 watt dummy load. So this is the bench 2950 that we're using, which, amp off, hello, produces yay to weed a little no watts on 12 volts. Hello, seen about 400 watts, 380 watts, hello, 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 hello. Going on, going out, and this is at 12 volts. I can turn the voltage up. Let me run the voltage up. So two things happen. The voltage on the transistors come up, and then the voltage on the transistors in the finals of all the radios, when I bring the voltage up to 15, that's a huge voltage difference. 3 volts. Hello. Now we're doing about 550 watts with 20 watts of drive. We'll go look at all the other accoutrement meters here that I show every video for a reason. This is the 5 watt slug and reverse with the 2950 down through the coax into the amp. Hello, 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 hello. We got a good input signal with only 20 watts worth of signal. No reflect. If your reflect is high on the input on the amplifier, you're going to end up having a little bit of harmonic issues that take place on the output side. Okay. This is what I don't like. A little bit of it. I have a feeling that when I go and throw a carrier, we're not going to see a whole lot of excess harmonics. First, second, and third order harmonics. We're just not going to see it. But when I modulate it up in power, we're going to see some second and third order harmonics. We're just going to see it. It's going to be there. They're going to be down here in this lower half of the scale, but it's twofold. You got to look at this twofold, right? You got to understand the fact that, once again, we might be overloading the receiver in the spectrum analyzer a little bit, and where those frequency humps are at comes into play too. So there's our principal carrier. All right. Well, let's look at this again. Amp off, amp on. Amp off, amp on. Let me walk around to the other side of things here. So now let's take and turn our dead key up. We're starting to see it a little bit. All right. Now we're at 100 watts unmodulated carrier. We're starting to see right here that we've got ourselves a little bit of love going on. But look at how far down that is from our principal. Okay. So let's modulate this real quick. Still 35 dBms down. We can see our sidebands that are starting to pop up over here. All right. Now that's with the transistor only being driven to 1/4 of its total saturation point. You'll find in this world, when you start to saturate components with a bunch of signal, the noise over here that the amp starts to produce gets freaking sketchy, okay? So right now we're taking 22 watts, 25 watts, we're dividing that by 4. That power's going in and it's getting broke 4 times. And there's 4 receptacles for that power. 1, 2, 3, 4 transistors. Each transistor on its best day, according to the paperwork. Now remember, we're working with Chinese components where they literally put anything on the paperwork that they got to put on it to achieve the sale. I'm so glad that the world is deciding to leave China and we're bringing manufacture of shit back here to the United States, where there's a measurement system and there's a standard system, and if you don't meet that system, you're done. Okay? We are nowhere near reaching the top end of the saturation of these transistors. They are not fully turning on as far as input signal. Their class of operation guarantees that they're 100% on, but the amount of input signal that is going into the transistors is not there yet. So let's go ahead and let's do this. Let's grab the derail Striker 955. We'll take and turn off the 2950. We'll turn on the derail radio. We'll turn the amplifier off. We'll go back over here to our unit of measure. Hello, 1, 2. Hello, 1, 2, 1, 2, 1, 2. We're not seeing any other dirt. Not at this scale of measurement. The fact that I got to be so wide, it does show the other harmonics that go out further, but it does not allow us to see what's going on in the small picture. So at this form of level of measurement, okay, nothing. Now let's turn the amplifier on. Amp on, amp off, amp on. Let's modulate it. Hello. Oh my God. Oh my God. Oh my Lord Jesus, help us all. That secondary harmonic is the one that you have to really keep an eye on. We want to do whatever we can to help suppress that harmonic, because that's the one that's going to show up in reflect. The rest of this other stuff that's going on, when you look at it in real world operation, so I take and I tag this thing, beep, mark it, and it says it's at 75.6 megahertz. Then I actually go and get my radio and spool to that and go to listen for the signal, because there's a little bit of RF that leaks out as you're operating the amplifier. Right, it just happens. RF leaks out of the coax. It's called line loss. Unless I'm willing to go to hardline coax, which I don't want to even deal with, there's going to be a little bit that leaks out into the atmosphere. I go to listen for it and the signal's not present. Remember how we spent a little bit of time talking about how the front end of this thing can get overloaded because we're reading such a massive amount of signal, and this is designed to read stuff that's way down? Okay. The ones that are up here, I don't want to see them. I don't want that. I want to have clean RF. All right. We're going to do a one-to-one comparison. So we just showed this in operation with this radio, which we all know is clean, going into this amplifier with this current tune setup in it, going into the dummy load on a measured system. This is what we got for results. All right. It showed it on both radios. The frequency where it took place changed from radio A to radio B, but the quantity of the signal changed dramatically from the first radio to the second radio. The second radio, just for the record, let's show what we're putting into it for drive. Let's shut the amplifier off. Hello, audio. Hello, audio. About 110, 115 watts worth of input power. So now each transistor is seeing about 27, 28 watts peak, and probably 11, really close to 11 to 12 watts average across each one of the components. Let's go look at what we're doing on the average scale. It's about 25 watts on average, roughly. And we can't use really that low end of the scale. It's not really that accurate until we get up here into the top third because the bird meter isn't linear, blah, 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 blah. So the math tracks. Got good peak power, got a good average. We're getting close, but we're not oversaturating the transistor. We're right at that point. And we also got to take into consideration the thing that we're fighting is the HG transistor itself. They're not the Toshiba, but they're the best that we've got, and they work perfectly fine. But we can create a little bit better signal with the Toshiba with certain situations, with a certain amount of controls in the circuit. It's not as prone to creating auxiliary harmonics, but it's a conversation for another day. Anyhow, that's what we got. I'm going to change this circuit out, and let's see what happens. All right. So now what we've done is, let's go over here. Sorry, guys. What we've done here is we have changed out the flyback circuit to just a standard 100 ohm and 104s. Okay. Now we are on, let's turn the amp off. We are on the 2950. Hello, 1, 2. Hello, 1, 2. So they're putting about 20 watts in it, 25 watts in it. Hello, 1, 2. Okay. Now we'll turn the amp on, and we're going to see that before we were barely able to achieve 500 watts of power, right? Producing a smidge more. So now let's go over here and let's look at the boxes. So once again, radio, amplifier, radio, amplifier. Hello, 1, 2. Hello, 1, 2. It's trying real hard right here. Hello, 1, 2. But we're talking that is 10, 20, 30, 40, 50, 60, or pardon me, shoot, that's 43 dBm down from the principal. So we're way down in the basement. Now what we're going to do is we're going to switch over to the other camera. Let's go ahead and slide over here to the other camera. So here we are at the other camera. Now we're looking at this. This is the outside world. It's hooked up to my big beam and whatnot. Slide it out to the outside world. So this is our noise floor. Right now I've got a lot of noise. We're at about 3 or 5 dBs worth of noise across the scale. This is 250 kilohertz wide. Okay, so a total of 500 from here to here. Each one of these boxes, so 10, 20, 30, 40, da-da-da-da. You get it? So right now, leaking out in the atmosphere. And what I mean by leaking in the atmosphere is I don't think that even if you were parked at the end of the street that leads to where this shop is at, you'd be able to hear any of this. Even no matter what I did over here for power, because everything's bonded, sealed, grounded, and everything. See that? That's the radio. That radio, I'm going to change the frequency on the radio instead of changing the receiver. Okay. This is just the radio right now. Hello, 1, 2, 1, 2, 1, 2. So we're putting 25 dB in the receiver. And that's because the antenna is right here. We'll add 6 dBs, then we'll add 12 dBs to it. So we don't overload the receiver. Otherwise, it's going to give us a false reading. It's going to show that we're occupying more bandwidth than what we really are. Hello, 1, 2, 1, 2, 1, 2. Let's go ahead, we'll knock that on down. We'll go all the way down to 18 dBs worth of attenuation. Hello, 1, 2. As you guys can clearly see, I'm only occupying maybe 2.5 kcs that way and 2.5 kcs that way, all right? So, let's go ahead, we'll turn the amp on. Now check this out. Amp's on. Hello, 1, 2. Hello, 1, 2. As far as this receiver is concerned, 100% of my energy that I'm trying to utilize coming out of the amplifier is present here. It's not, there's no second order, third order, not even up and down 1 or 2 channels. That's my wife. Hold on, you guys. I'll be right back. Okay, we're back. Sorry. There's very few people on this earth that I'll stop doing video for, and it's one of them. I mean, most important thing in the world to me. So, okay, so like I was saying, even at this oversaturated signal point, it's still showing us that we're occupying no, like, spurious emissions are taking place, right? Hello, 1, 2. So maybe 6, maybe at the most, maybe 8 kcs wide. So, I don't know. You take from this what you want. Let's go ahead. We'll switch over here now. We'll go to the striker radio, so we can have a really good A to B. And you know what? Let me get the striker hooked up. And then through the power of cinematography, I'm going to take you back, and we're going to look at what it looked like on the spectrum analyzer on the 2950 before and now. Okay, so off 2950, and now we're on to the 955 radio, the striker, universally accepted #1 hottest radio in the world right now. All right, let's grab our microphone. Now, if we can remember, when we used the striker before, we were seeing huge harmonics. Okay. Amp off. Radio. Amp. Radio. Amp. Hello. Hello. Still 35 dBs below our principal, and far fewer harmonics at the saturation point of the transistor. So, and then we have this other weird odd side effect that takes place too. Seeing 120 watts more power. Now, I'm not going to lie. What causes the more power is the simple fact that this circuit is tuned to have this extra capacitance in play that we added in here. For us to have a 1-to-1 comparison ratio, what I'd have to do, I mean like legit full bore on the watt meter alone, I'd have to retune the output and retune the input to compensate for the lack of the capacitance that's in the circuit by using this wire system. Because all capacitance in the circuit matters. This has no reactive capacitance in the circuit whatsoever. This does. So I'd have to compensate for that with the input and the output tune on the amplifier. But as far as this is concerned, that adjustment is not going to make that big of a deal to this result. So I just wanted to cover that. Okay, let's go look at it on the other radio. All right, so there's our receiver. There's the radio. Hello, 1, 2. Now let's bring the amp into play. Hello, 1, 2. Looks about like the same frequency occupation. So, I mean, I also want to show you this. When I turn the attenuator off, noise floor comes way up, of course. But then let's take a look and see how that affects our overall signals. Radio, hello, 1, 2. Hello, 1, 2. Still not that bad. Now we've gone from overloading the receiver and the radio, and we've gone from occupying 5 or 6 kcs to about 8.5, maybe 10. I think you get where I'm going with this. Okay, enough with the other radio. Let's get back over to this. The unit of measure has been made. I'm not saying pro and con. I'm not. I prefer this style of flyback circuit. I feel it's a little bit cleaner. There's arguments that can be made either way. I'm just putting it out there for general knowledge, and people can take from this what they want from this video. I'm not saying it's bad, because like I was saying, you can take, and you have a thing called resonant integers, right? So like if you have your principal here, at another divisible farther down the scale, you're going to have yet another resonant point for, like, let's say you're going to have like a half wave antenna, and you go up in frequency another integer, you'll go over, and that half wave now is a full wave at another frequency, and so on and so on and so on. So you can sneak in some second and third order harmonics, and it's not going to show up over here on your watt meter as excess reflect if the frequencies that are being produced by the amplifier are within the resonant spaces for the different. I think you guys get where I'm going with this. Okay, we're done. Little test portion of this is pretty much over. What I want to do now is I want to play with the input tune on this a little bit, play the output tune on this just a little bit, polish it so it's perfectly perfect. And when we come back, we're going to do the total watt demonstration for this amp. We're going to show the input output, and then we're going to put the lid on it, get the fan all running on it, and it's ready to go to a new home. We're done. End of the conversation. So let's go over here. Let's do the meter dance, as I like to call it. So radio drive, we're on 15 volts, of course. Hello, 1, 2. Hello, 1, 2. Okay. 120, 130 watts. Hello. Hello. Off the scale. Hello. Off the scale. Hello, audio. Now, let's go over here and let's look at the other side of the thing. Hello, 1, 2. Hello, 1, 2. Those are real numbers, y'all. So 0.2 of a watt worth of input reflect. Hello, 1, 2. And 1 bar on the striker gets us, hello, 1,000 watts, no problem all day long. Now, as you guys can clearly see, this amplifier comes with a coarse quick disconnect 175 amp Anderson connector with a big power disconnect. Here's our drop hammer forged fan guard. It's going to be on top of the fan. I'm thinking, because I had some prices go up, the power wire went up and a couple of the other things went up. I think I'm going to need to get $835 for this, and I'll even cover the ride. So $835 out the door, and she's yours. Masterclass number 39. Gentlemen, you guys know the name, the number, and the whole song and dance. I want to say thanks Siglant, thanks Mechman, thanks Bird, thanks XS, thanks Coaxial Dynamics. Thank you to all the YouTube subscribers. That's you guys. And then thank you for the Patreons. My guys on Patreon are pretty awesome. It's a pretty active group. Got a lot of posts, a lot of stuff going on over there. If you've ever learned anything from me, anything that's ever helped you complete an amplifier or be able to get your amp fixed or anything, please come over and show the channel a little bit of support. Google just started this new thing where they expect you to sign over any and all copyrighted merch, logo, designs. They want a portion of it. And I said, no, I'm not going to agree to that. It's like they would want a little bit of everything that's got a logo on it. And they say that they have claimed full right to that if I sign this little piece of paper. They'll pay me a whole lot more money, but I say no. I don't want to be a slave to the almighty, all-seeing, all-hearing Google master, so I've decided to not participate in that portion of the ad revenue generation system. So if you could, be kind and come help out the channel, I'd really appreciate it. Come join us on Patreon. I'd really, really, really thank you for it. You guys got to remember, I do these videos not for me. I already know all this stuff. I do it all for your guys' entertainment and your learning pleasure. So I say thank you once again for watching. At the bare minimum, please give me a thumbs up for God's sake. It helps with the YouTube algorithm by a ton, apparently. So give me a thumbs up, and I want to say thanks. So I'm going to put the lid on this thing. We're going to get it all boxed up and ready to go to its new home. Gentlemen, like I said, Masterclass number 39 in the history books. I'll see ya. Click, click.